So let's first recap on how to set up the partial fractions. So if let's say you already tried to factorize, right, the denominator from, let's say, a quadratic or a cubic polynomial, and then you realize that, for example, here the factors are linear and also distinct, meaning they are different from each other, then it will be this case where you can just put down your denominator as x minus 1 and x plus 2, for example. And then in the numerator, you just leave it as a and b like that, right? So remember that the highest power of your numerator must be less than the denominator, right? So since the denominator are linear expressions, then in your numerator, it is just a constant. Okay, so in some cases, you have linear, right? And then you also have a repeated linear factor. So how do you recognize this? So in this case, there will be a square outside of the bracket containing the linear factor. So in here, you have x plus 2 as the linear factor, but outside of the bracket, there is also a square, which means x plus 2 square is actually just x plus 2 times x plus 2. So this linear factor of x plus 2 gets repeated. So a telltale sign would be to see that, okay, your bracket, outside of the bracket, there is actually a square, right? So in this case, then you do need to remember to put in something which I will put down on the screen later on. So here you need to put b over x plus 2 first before c over x plus 2 square. Now, one way to look at this is, of course, there are more complicated ways to look at this. One way to look at this is you can think of it like your 1/4. So decomposing the 1/4, it can actually become half minus a quarter, right? So it is somewhat like this situation. So think of it that way, then it doesn't seem very unfamiliar, right? And then also in this case, why do I use this example? Because 4 is actually a perfect square. Okay, so next I will move on to the last case where you have the irreducible quadratic factor. So how do I identify this? So basically, for this form, irreducible quadratic factor, it means I have this x squared plus 2 where I cannot further factorize. So from the start, I mentioned that you try to factorize the expression in the denominator, and then until the point where you can't factorize anymore, and sometimes you still have a x squared inside this bracket. Like in here, you have x squared plus 2, and you cannot actually factorize anymore, so we consider this as irreducible. And one telltale sign of this sort of form is that it's a bit different from the repeated linear factor case, where in repeated linear factor, right, you have the square outside of the bracket, whereas in this case, you have the x square here, and then you don't see the square outside of the bracket. Okay, so for this case, first of all, like if you still have a linear factor, then you still put down x minus 1 in your denominator, and in the numerator you put a. But take note that for your denominator, because of the x squared plus 2, this is quadratic, right? So your numerator will have to be linear. So you put down bx plus c. All right, let's look at why is there an additional b over x plus 2 for the case of repeated linear factors. Right, so let's say I treat the x plus 2 as u, right? And so the denominator will be x plus 2 square become u square. And remember that for the numerator, the highest power has to be 1 less than that of the denominator. So it will be bu plus c. Alright, so again, replacing the u back with the x plus 2, then we will have b times of x plus 2 plus c, right? And then in the denominator, of course, replacing back with the x plus 2, then we will have x plus 2 square. And then when we split them up, we actually get b times x plus 2 over x plus 2 square. And then of course, realizing that for the second fraction, we actually can divide x plus 2 top and bottom. So basically we cancel this out, all right? And that's how we arrive at b over x plus 2 in the middle for repeated linear factors. Before we begin with our partial fraction decomposition, we always need to be doing this first. We need to check the degree of polynomial in numerator and denominator, right? So what is this degree of polynomial? Basically, it is the highest power of x in the polynomial. So let's say if the degree of numerator is less than the degree of denominator, then the fraction is proper and we can continue with partial fraction decomposition, right? So one simple example would be this. In numerator, we have 3x minus 2, so the degree is 1. And in the denominator, if we expand that, we're going to get x times x, which is x squared as one of our terms, and that gives us the highest power of x, which is 2. Right? So since the degree of numerator is less than the degree of denominator, then we proceed with the partial fraction decomposition. However, if the degree of numerator is equal to or larger than the degree of denominator, then this fraction is improper and we need to perform long division first. So for example, over here, we have the degree of numerator as 2, and in the denominator, it is again the degree of 2. So since the degree is equal for both numerator and denominator, then we say that we cannot proceed with the partial fraction decomposition, so we need to perform long division first. All right, and likewise for this, the degree of numerator is 3, and in this case is obviously larger than the degree of denominator, which is 2. So therefore, we also cannot proceed with the partial fraction decomposition, and we need to perform long division first. And I will go through a little bit more in detail towards the end of this video. So for the first case of distinct linear factors, what we did earlier on is to set it up as a over x minus 1 plus b over x plus 2. So the first thing that we'll be doing is actually to make a common denominator on the right hand side, right? So the objective of doing that is that on both sides, then there will be the same denominator, so basically we'll just compare the numerator. So we can just multiply x plus 2 in the numerator and denominator for the first fraction, x minus 1 in numerator and denominator for the second fraction. All right, and then moving on from there, I'm going to write the same thing here. And notice that on both sides, the denominators are the same. So we basically just compare the numerator, okay, and we drop the denominator completely. Okay, and now we are able to form our identity. Next, what we want to do is to, for example, either set this to be 0 or set this to be 0 in order to solve for each of them. So that's what we'll be focusing on. So in order for me to set this to 0, what I need to do is to basically replace the x with negative 2. So the first thing I will do is to sub x equals to negative 2. And what that does on the left hand side is I just sub the negative 2 into the left hand side. And on the right hand side, we still write out our substitution. Even though we know that's going to become 0, we still should show that. Here we have b times of negative 2 minus 1. And then on the left hand side, we have negative 8 equals to, on the right hand side, it will be negative 3b. Right, and solving for b, we will get 8 over 3. Now for in terms of working your algebra, and because you're going to eventually be putting that back to the fractions, you should leave this as improper fraction, right? In terms of algebra, it is more, it's easier for you to manipulate. So it's easier for you to manipulate improper fraction in the algebra sense, all right? And so next thing I want to do is, now that I already know the value of b, so obviously I'm going to solve for a, right? So as mentioned, I also need to make this become 0, so I'm going to substitute x equals to 1. And of course, I already know b equals to 8 over 3. And then that's what I'm going to sub in as well. It's just for formality, so actually it doesn't really matter because you're going to make the x minus 1 equals to 0 anyway, but just for clarity I put that down. So 3 times of 1 minus 2 equals to a times of 1 plus 2 plus b is actually 8 over 3, and then you have 1 minus 1. All right. So again, like I say, it doesn't matter. The b is 8 over 3 because 1 minus 1 is going to give you a 0. So what you have is 3a, right, equals to 1. And then solving that, we will get a equals to 1 over 3. Now, up to here, you're not done yet. This is not the final step. You still need to show the decomposition of the original fraction. So you should still put it back to that. Right, and that's equal to 1 over 3 over x minus 1 plus 8 over 3 over x plus 2. Now you can't leave it like this because you cannot have a fraction in the numerator or the denominator for the matter. So I just want to use a very simple situation for you to understand what I'm going to do next. So basically, if let's say I have a number 4 over 3, right? I can also say that this is the same as 4 times of 1 over 3. And how is this relevant here? So what I'm going to do is to transform it to the form that we need. You can see it as this. You are actually taking factorizing out the 1 over 3, and then you're left with 1 over 3 times of x minus 1. And in short, if you multiply the numerator with the numerator, denominator with the denominator, you actually end up with this. You actually end up with 1 over 3 times of x minus 1. So you see what I'm trying to drive at. So basically, for the second fraction, it will just be 8 over 3 times of x plus 2. And that concludes our first case of distinct linear factors. For the second case of the repeated linear factors, we set it up as a over x minus 1 plus b over x plus 2 plus c over x plus 2 squared. Alright, so for this case, we will still do the same. We'll try to make a common denominator on the right hand side, and then furthermore, I actually combine them into one single fraction straight away, so to cut down on our steps. Alright, so we need to observe for each of the three fractions on the right hand side, what is it in the denominator that we lack in terms of the factor. So for the first fraction of a over x minus 1, we need to multiply numerator and denominator by x plus 2 squared, alright, in order to have a common denominator. For b, you need to consider that the denominator doesn't have x minus 1, so you multiply x minus 1 in the numerator and denominator. And also, although it has x plus 2, but the third fraction has a denominator of x plus 2 squared, which is repeated. So you still need to multiply x plus 2 in numerator and denominator for the second fraction. And then finally, for the third fraction, the denominator is missing a x minus 1, so I'm going to multiply that in numerator and denominator. So after we compare the numerator, what we will have is 3x minus 2 equals to a times of x plus 2 square plus b times of x minus 1 times x plus 2 plus c times of x minus 1. all right? So the subsequent step is very similar to the previous case. So what we will first do is try to observe what we can substitute in for the value of x, and then here let's try to observe that I actually can substitute x equals to 1, and this 2 will become 0, and so therefore if I have 0 times c and 0 times b, both b and c will disappear, right? So what you do is to substitute in x equals to 1. On the left hand side we have 3 times 1 minus 2. On the right hand side, all right, we will have a times of 1 plus 2 square plus b times of 1 minus 1 times 1 plus 2, and then we will also have c times of 1 minus 1. So of course, this becoming 0 and this becoming 0 makes b and c disappear, and what we will have now is only 1 equals to 9a. So solving that, we'll have a equals to 1 over 9. So next, we will substitute in the a equals to 1 over 9, all right? And we now want to eliminate either b or c. So observe that if I substitute in negative 2, we'll have negative 2 plus 2, which is 0, then b will disappear, leaving us with only c, right? So what I'll do in the second substitution is actually to sub in x equals to negative 2. So we'll have this, right? So here, after we sub in, so observe that this becomes 0 and this becomes 0, leaving us with just c, right? So, and that's what we want. So here we have negative 8 on the left hand side, and then on the right hand side we have negative 3c, right? Solving that, we will have 8 over 3 for the value of c, right? And then that leaves us with the final one to solve for, and that is b. Okay, so for the final one, you don't have to scratch your head and overthink about this. So first of all, a is 1 over 9 and c is 8 over 3, and same thing, I will put in the a and c first. And here we will not overthink, and we'll just use a very convenient number, and we're going to substitute in x equals to 0. All right, and what that does is, in fact, in this case, you can actually just submit any value of x, and that's fine because we are only down to only b that we don't know yet. All right, so a very simple number, straightforward to submit and evaluate would be x equals to 0. So we have this, and this, and so on. So after we substitute in x equals 0, and we do a bit of rearranging and solving, which I won't elaborate, then we'll have b equals to negative 1 over 9. So as seen before in the first case, all right, I will go a bit faster this time around. I'll just say that if this is 1 over 9 for a, then we simply can just put it as 1 over 9 like this, and we have b is negative 1 over 9, and then c we have 8 over 3, right? So this is the partial fractions for the second case of repeated linear factors. So for the case of irreducible quadratic factor, we set it up as a over x minus 1 plus bx plus c over x squared plus 2. So for the first fraction, notice that the denominator doesn't have x squared plus 2, so we multiply x squared plus 2 in numerator and denominator. For the second fraction, we don't have x minus 1 in the denominator, so we multiply x minus 1 in numerator and denominator, right? So notice that for the right hand side, the denominators are now common denominator, so therefore we combine them together, and furthermore we compare the numerators we get 3x minus 2 equals to a times of x squared plus 2 plus bx plus c times of x minus 1. Next, we want to try to make this x minus 1 become 0, because if this is 0, 0 times of bx plus c will make both b and c disappear. All right, so the first thing we do is to substitute in x equals to 1, and throughout we substitute in x equals to 1, and then what we will have is 1 equals to 3a, and then a equals to 1 over 3. Then the next thing I do is to substitute in a equals to 1 over 3, and then I've done it here. And we now want to make either b or c disappear. So the easy one to make disappear is this b, because if we substitute in x equals to 0, then b times of 0 will make b disappear, leaving us with only c. All right, so the second thing we do is to substitute in x equals to 0. And what we have here is, on the left hand side, we have negative 2. And we also have 2 over 3 plus b times 0 means b is gone, leaving us with only negative c, right? So it's actually 2 over 3 minus c. And solving for c, we actually get 8 over 3. So for the final one, which is b, I'm going to do it slightly different. I'm going to introduce the comparing coefficient method to look for b. All right, so of course we can also sub in some values of x to find b. However, I just want to introduce a different way of doing things, so to freshen things up. All right, so here, notice that we only want to look for b, so let's try to target something. All right, so let's try to target bx times x. All right, and that's going to give us bx squared. So the objective here is actually to go and compare the x squared terms. So notice that we also have ax squared, and on the right hand side, that's the only way we can get x squared terms. On the left hand side, there is no x squared term. So that means the coefficient of x squared on the left hand side is actually 0. So by comparing coefficient of x squared on the left hand side is actually 0, on the right hand side is actually a, and plus bx times x is actually bx squared, so the coefficient of x squared is actually just b, and since a equals to 1 over 3, then b equals to negative of 1 over 3. So now we can put down our partial fractions. And first of all, we have 1 over 3, which of course, as mentioned before in previous cases, we can actually write it as 1 over 3 like this. So we have 1 over 3 times of x minus 1. But the second fraction is slightly more tricky in a way. So what we do is to do this. Right, so we put in the bx plus c accordingly, and what we do here is to actually factorize out a negative 1 over 3. So what we do here is actually to factorize out negative 1 over 3, then we'll be left with x inside, and then of course when we factorize out a negative number, this is going to give me a minus. All right, and we're left with 8. So therefore in the numerator we're left with x minus 8, and in the denominator we have the 3 times of x squared plus 2, and of course remembering that we have already factorized out a negative number, this becomes a minus. And so that's it for this case of irreducible quadratic factor. So we come to the last part of the video where I want to make a quick mention about what happens if the degree of numerator is equal or larger than that of the degree of the denominator. So as mentioned earlier, we need to first perform long division, all right? So in this example here, we try to perform long division, but before we do that, we need to expand the denominator first, all right? And we have x squared plus x minus 2. And then another thing we need to do is that the 3x squared minus 2, we actually have a missing term. So adding in the plus 0x will help us with the long division, all right? So in order for us to remove the 3x squared, we need to take 3 multiply with x squared to get 3x squared here inside the bracket. And then 3 times x will be 3x. And 3 times negative 2 will be a negative 6. So I put a negative 6 here. And we'll be left with negative 3x plus 4. So all in all, we will have 3 plus negative 3x plus 4. In case you wonder, do I need to factorize out a negative 1? You don't actually need to. You can leave it to the end. If let's say the A and B are negative, then we can always factorize out the negative later on, right? But for now, just focus on this fraction and perform your partial fraction decomposition. All right. So I've reached the end of this video. I hope this video is a comprehensive enough guide for you to get started on how to perform partial fraction decomposition. And all the best to you in your learning, and hope you can perform your partial fraction decomposition with confidence.